All right. They're probably not going to ask you a question like this, but it does show up in terms of torque and other things as well. So I want to give you a little bit of background on how to figure this out. So there's a place where you can put this positive charge where it'll be balanced by this negative charge and this negative charge because they're both attractive. It's very much like the Lagrangian points I talked about, where you could put a spaceship between the Earth and the Moon at certain places, and it would just stay there because it'd be being pulled equally by both the Earth and the Moon. So what we're saying is that the magnitude of F12, so Q1 and Q2, is equal to the magnitude of F23. And so I would say that K, Q1, Q2 over R12 squared is equal to K, Q2, Q3 over R23 squared. So I just numbered the charges based on how they were in the diagram, and I numbered the distances, which I don't know, but I know the total distance is 0.4, which I'll get to in a second. All right, I can make my life easier. I can simplify this. How can I do that? Because there's things that cancel out. It turns out that the thing you're balancing in the middle, it doesn't matter what charge it is. So whatever I can balance there is going to be balanced no matter what its charge is, which is the same thing with the Lagrangian points. We don't define the Lagrangian points based on what mass it is. The mass cancels out. So Q2 and Q2 go away, and so does K. The next thing is, I don't know what R12 is. I don't know what R23 is, but I know that R12 plus R23 is 0.4. So what do I have to do? I need to make one of the distances x and one of the distances 0.4 minus x. All right, so I'm going to rewrite this with the values in there because I'm going to make this nastiness go away too. So I have Q1, which is going to be negative. I don't care. It's going to be 5. Oh, that's there. Nanocoulombs over x squared is going to be equal to 2 nanocoulombs over 0.4 minus x squared. Now, what I'm going to do to make my life easier is two things. One, I'm going to get rid of this nanocoulomb, which is times 10 to the negative 9, because they both have it. So multiply both sides by 10 to the 9th. Go on. And instead of multiplying all this stuff out and foiling and using that, I'm going to square root both sides. And that's one of the beauty things about math is as long as you're fair, as long as you do it to both sides of the equation, you're allowed to do anything. All right, so when I rewrite this, I'm going to get radical 5 over x equals radical 2 over 0.4 minus x. Messy, but solvable. So I'm going to cross multiply, and I'm going to have radical 5 times 0.4 minus radical 5x is equal to radical 2x. I'm going to add my radical 5x to the other side. If you had a better teacher, he would have picked rounder numbers. Right? And then I'm going to factor out the radical 5 plus radical 2 times x. Yeah, somewhere else in the world or the country, there's a problem just like this, where it's radical 9s and radical 4s, and everything doesn't need to be messed with. And so we're saying that it is 0.245 meters from Q1. Now, timing-wise, they're probably not going to have you do something like this, but there's easier case ones where things aren't squared where they will. But I just wanted to show you that. All right, so electric fields are not on the AP exam, but I feel like they're useful for circuits, and the state of Ohio does say we need to know it. So if we fast forward to the early 1800s, and the Coulomb's law force thing was the very late 1700s. So that's right when they did the SI units. One of the more popular things to do was to actually go and watch famous scientists give talks and do experiments. So again, no television, no radio, no cell phones. And the people that were educated were people of high standing in society. Michael Faraday was not one of those people. So he was a bookbinder. He didn't make it out of grade school. So out of middle school, I guess, would be the equivalent if you guys didn't go to parochial schools. But he read everything that came through the bookbinder. And he was really interested in science, and he went to see the preeminent, most famous scientist of the time, Humphrey Davy, who you guys might know from discovering benzene. And he took notes of his lecture, and since he was a bookbinder by trade, bound them into a beautiful thing and presented them to Davy. And Davy hired him as an assistant to work around the lab. So even though he wasn't from standing in society, he helped around the lab, he helped with other things. Humphrey Davy blinds himself doing an experimentation, and Faraday takes over more, and a lot of what we know about early electricity is due to that. And he exceeds Humphrey Davy's fame, as we'll see, and invents the first electric motor. So because these public talks were a big part of being a scientist at the time, Michael Faraday wanted to find a way to explain what was going on between these charges that were interacting. And it was a big problem for people of the day, for a normal person, that one thing could exert a force on another thing and be so far apart. This action at a distance was tricky. They had problems with that. And that was another reason with Newton, too. Newton with the Earth and the moon, it's the same thing. And so what he did was he made up this idea of thinking that anything that had charge had this field around it. And it extended to infinity. And anything else that had charge that came into this field would feel this force. And he called the direction, or defined the direction, as being in the direction that a small positive test charge would feel. So an electric field from a positive charge would go away from it, because a small positive test charge would be repelled from it. A negative charge would be attracted, or would attract a small positive test charge. So those field lines go towards. So these start on positive charges and end on negative charges. Their concentration, or how many of them there are, will tell you how strong something is compared to another charge relatively. They extend to infinity, and they can never cross. So that field at that given point will give you what the force any charge would feel at that point, and a charge at any point would only feel one net force, even if there's multiple charges. Now, these field lines do not go through the charges. And that's a big difference between charge and magnetism. In magnetism, the magnetic field goes completely through. Which again, magnetism is another topic that's not on the AP exam that I would like to cover. So, a negative point charge, equally spaced arrows, all going towards. A small positive charge would be attracted to it. A positive test charge, or positive point charge, arrows going away from it, equally spaced. A small positive test charge, no matter where it was put, even where there wasn't arrows, we would know that it would go away from it. And we'll do this in effect. You guys are going to do a lab on this where we're going to look at universal law of gravitation, Coulomb's law, and electric fields. All right, these are both positive charges. I'm saying one is positive 4, one is positive 1. If I count the number of field lines from the smaller one and I have 4, and this one is 4 times as big, you would expect that there would be that's right, 16. So 16 field lines going away. If you have 2 positive charges, there's going to be an area in the middle where our electric field is nothing. It's going to cancel out. It's going to go away. If we have like charges, they work together. So a positive test charge would be repelled from this side and attracted to that side. If you put these on a plate, and you have a place where you can enter charges in the end, you get an electron gun, which is how energy is given to particles and particle accelerators. Also how early televisions work, like tube ones like I have in the front of my room. That's why they're so long. There's an electron gun in the back, and it's shooting them across a potential, giving them kinetic energy, and then those electrons are bent by magnetic fields. So a couple of things about electric fields. Because on a conductor, all of the charge resides only on the surface. There's no charge inside. Everywhere inside the electric field is 0. That's not the case if you have an insulator. So an insulator, the charge is going to be wherever it is, so your electric field would not be 0 inside. So this is why you're safe in a car in a lightning storm. If your car got hit by lightning, the charge would go from the outside of the frame of the car down to the floor, or possibly from the ground up the frame, up into the sky, whether the lightning is coming down or going up, and both happen. Even if you were in a metal train car, where the tracks are metal, the wheels are metal, the axles are metal, you're standing on metal, you're touching the sides that are metal, the top is metal, you would not get shocked. It would go around the outside of you. This is known as a Faraday cage. So the charge only goes on the outside. This goes against common sense. You would think that if it's getting hit by lightning and I'm touching that metal, it's going to come to me. It's not. And it makes sense why it would not, because you're not a very good conductor. If that charge can go through the outside and go right down to the ground, why would it go through you? This electric field is given by KQ over R squared. Now, to get this back to Newtonian mechanics. So let's connect this to something we already know. So how we learn things. We have our electrostatic force. That's K, Q1, Q2 over R squared. We have our gravitational force. That's G, M1, M2 over R squared. We have an equation that looks just like this. And it's that little g equals Gm over R squared. So our electric field the magnitude that we feel from a charge. Our gravitational field, the acceleration due to gravity we feel, the gravitational field strength is a product of this constant, big G, the mass. We have our Coulomb constant and our charge divided by R squared, divided by R squared. The units for this are newtons per coulomb or volts per meter. And again, this isn't on the test, so I'm not going to go into great depth on calculating, but it does relate to gravitational field strength as well. All right, so charges plus Q and negative 4Q are situated as shown above. The net electric field is zero nearest which point? So to cancel these out, because one is 4 times bigger than the other, you're going to have to be twice as close to the smaller one. The electric field from this one is going to go away on both sides. The electric field from this one is going to go towards on both sides. And so, A, right? So from negative 4Q would be an electric field that way, from positive Q would be an electric field that way, and this distance here is twice the distance there. Diagram above shows an isolated positive charge Q. Point B is twice as far from point Q as point A. The electric field strength at A to the electric field strength at B is. If you double the distance, the field is going to change by a factor of 4, right? Electric field, just like gravitational field, just like electric force, just like gravitational force, is inversely proportional to R squared. Adding vectors, what is the direction of the net electric field at point P? At point P from this one, it would be a field going away. At point P from this one, it would be a field going away. The combination of these two arrows would be a diagonal in that direction. And you'll see that in the fact. If you have two plates that are charged like this, they're going to have a uniform field inside. That means that it's constant. Because these fields extend to infinity, close to the edges, it's going to curve out, and it's not going to be uniform. And so this curving is known as edge effects. In physics, these are mentioned just so that they can tell you to ignore edge effects usually. To find out what this force is in a uniform field, you can say that F is equal to E times Q. And we already defined electric field as the force divided by Q. Just like we defined the gravitational field as, I should put E here, right? I just canceled out a mass, right? We got the gravitational field strength. So this would be how an electron gun works. That's actually the guy's beard. It was a question that was in the textbook at some point.